Welcome back, everybody. Hope you had a great start of the week. Now, one thing I just wanted to say is a technicality about the lecture material, because if you look at the Jupyter Notebook, there are some small differences between the Jupyter Notebook and the PDF file. And that is simply because there are LaTeX packages which you cannot use with MathJax. And one of these is about contractions being used with second quantization and expectation values, etc., etc. So you will notice that there is some additional material in the PDF file with respect to the Jupyter Notebook, simply because MathJax doesn't have support for all the kind of fancy LaTeX packages which you can get. And the contraction and Wick's theorem related stuff is something which you will not find in MathJax. I haven't been able to fix it. So if somebody knows of a fix, that's very, very welcome. So today is going to be what we are going to call a number representation or second quantization bonanza. So we are going to discuss different things like the operators in second quantization. And I want to go through the derivation of at least a one-body operator. And when you see that derivation, which is perhaps not so exciting, the one with the two-body operator is just a kind of replica of that, with lots of subscripts and indices to keep track of. Then we are going to look at examples. We are going to introduce what we will also call a diagrammatic representation. So when you do many-body physics, and for those of you who are familiar with quantum field theory, representing many of these operations with pictures and what we often call Feynman diagrams is something which we are going to introduce gradually, because that gives us a very compact way of expressing physical processes. Then tomorrow, or perhaps towards the end of the day today, depending on how far we are, I wanted to go through Wick's theorem, and that is the time-independent variant. Later, if we have time, we will look at the time-dependent variant, and for those of you who are following a course in quantum field theory, you will encounter the time-dependent variant of Wick's theorem. So Wick's theorem is extremely handy for us, and what I'm going to do now is actually go to the very end of these slides and but in the beginning, just remind you of things we discussed last week. So we have the so-called anti-commutation relations between the creation and annihilation operators. And we also defined these operators in terms of an operator acting on a true vacuum, which we later will redefine in order to simplify further the calculations. And this acts on the true vacuum, and it creates a particle in a given single particle slot, where alpha points to specific quantum numbers. Then we can create a many-body state in terms of these creation operators. So this is just a quick reminder from last week. And then we also had the Hermitian conjugate of the creation operator. And that is an operator which removes a particle from a given state if that state is occupied. If not, it's equal to 0. And then we have the final commutator algebra, which is given by these expressions here. Now, one thing which I wanted to do when we've gone through this, I wanted to quickly remind you of what we did last week, because last week we stated Wick's theorem, but we didn't make derivations of it, but we showed Wick's theorem for one pair of operators, which is an annihilation and creation operator, and two pairs of operators. And we calculated some transition probabilities and expectation values with that. So the theorem is based on normal ordering the product. And you will see that in the literature, there are different ways of writing this normal ordering. So I'm bringing up one, which we didn't use in the lecture last time. So let me just quickly say something about that, so that this doesn't come as a surprise to you guys when you look into textbooks. So let me just do that. So sometimes what you will see is that this normal ordering, let me just quickly remind you of that. And I'm going to bring up the slides again. You will see a notation. So when we are looking at the chain of operators, we have now a chain of operator where we are forcing a normal ordering. So we have this can be a chain of operators. This is one way of writing it. Another way, which you will encounter in the literature, is something like this: X, Y, C, like that. Or alternatively, it may be written like this: X, Y, C. We will come back to when the latter one actually pops up. So this is often, the latter one is often used in connection with the redefinition of the vacuum state. We will come back to these technicalities, but some textbooks use the middle notation. Other ones, like we did in the lectures last week, we just used N. So, but let's just go quickly back to the slides this week and go through some of the things which we discussed without a proof. So if you look at the expression here, what we have now is a normal order product where we simply switch the operator so that we have at the end a set of creation operators to the left and annihilation operators to the right. And this P here is the number of the permutation that are needed to transform this original string. And then we have a contraction, which is actually the same as this vacuum to vacuum expectation value. So this is between two operators. Then we set up the, we just stated Wick's theorem without proof. So you can actually also contract operators inside the normal order products. And this is normally defined as the original relative position between two operators in a normal order product, as P. And that's the so-called permutation number. So you have to permute some of the operators so that they get close to each other. And that leads to a set of permutations, which we have to do then. And that leads to a prefactor here. Wick's theorem, if we now have a chain of operators, then we have a normal order chain. So when we calculate an expectation value, so what is often common to do now is that on the left and the right here, we skip the states we are calculating the expectation value with respect to. So in principle, what you should put here is a state here, normally the vacuum state, and its Hermitian conjugate here. This is normally skipped just for compactness of the equations. And this is a normal order product. This is the sum of the normal order products where we have all just one pair of operators contracted. So all these terms here, till the very last one, all these ones are exactly equal to 0 when we calculate a vacuum to vacuum expectation value. So that means that the only thing we need to calculate then is the normal order product of all the possible contractions between pairs of operators. So that says that if we have an odd number of operators, this is automatically going to be 0. So that's Wick's theorem. And the sum here means that you have a sum over all terms with n contractions. And the term n divided by 2 means that the largest integer that would not exceed n divided by 2, where that is the number of creation and annihilation operators. When it's even, then the sum contains fully contracted terms. When it's odd, then there is something which is left uncontracted. And when you normal order it, it's going to give us 0. And this is something which we will discuss a little bit later here. And that's the generalized Wick's theorem. I'm going to come back to that one. So tomorrow, or towards the end of the day today, we are going to give a proof for Wick's theorem. But now we are going to look into some other technicalities before we move on. This is just to remind ourselves quickly of what we discussed last week. And I demonstrated this with one pair of creation annihilation operators and two pairs of creation and annihilation operators. And we saw that we could actually write this sum out as a sum for that specific case with a sum which would terminate at the level of two pairs being contracted. And that was a term which gave us something which was different from zero. So the proof of the Wick's theorem goes by induction. So if it works with 1 and 2 pairs, it also works with n+1 pairs, etc. But now we're just going to use this to get a little bit acquainted with what is going on. But the thing which I wanted to go through in somewhat more detail now is the translation of a operator into an operator which is defined in terms of creation and annihilation operators. So let me just bring this up. Now, in order to do that, there are some manipulations which we need to go through. And last week, we simply stated that H0 could be written as a sum over, let's say, we have a basis alpha beta, and then we have an integral here of H0 of beta, and then we have a creation and annihilation operator. So this is the number representation expression for the operator. So this is what we call an integral. Let me just quickly remind you of that one. So that would be an integral over a d of x, and then we have some phi alpha of x. We have an operator H0, which is normally kinetic energy, plus some external potential energy. Sometimes we have an orthogonal basis, which is also an eigenbasis of H0, and that reduces into a diagonal form. So if H0 times beta is equal to some energy times the state beta, then in that specific case, this sum reduces simply to epsilon alpha multiplied with A alpha, because then we obviously have a Kronecker delta between alpha and beta. So that's a further simplification, but we can just leave it like that without making an assumption that the basis we are having is an eigenbasis of H0. This is often a normal starting point when you do many body physics. Okay, the other thing which we stated, because we wanted to apply this immediately, so this is the interactive part, was then given by 1 over 1/2, and then we had alpha, beta, gamma, delta, and then we have an alpha, beta, so this is again an integral, gamma and delta, and this was multiplied with the creation operators. And due to the Pauli principle for fermions, these deltas and gammas change. So this is something which we will come back to. And then last week, we did some calculations where we used Wick's theorem without having gone through the proof. And we showed that we could actually come in a compact way, calculate expectation values with these forms of operators. But that means often that we have these expressions being tabulated, or that these quantities can be calculated quickly on the fly when we are calculating expectation values of a specific system. So when you implement this in a computer, what is pretty normal to do then, since these operators for fermions, they follow Boolean algebra, is that you can actually use Boolean algebra when you act on with this one on a state. And then when you have found the right indices, you will simply look them up in a table where you have stored these integrals. Alternatively, if these integrals can be calculated easily on the fly, you would do that in case you have a huge basis of single particle states. So that element which you see there is what we normally call the interacting matrix element. Matrix because we're going to store these as matrices. And then we have a V of x1, of x2 here, where we haven't specified what kind of interaction we have. and then we have x1, and then phi delta of x2. So the whole thing with the second quantization or number representation is that we have, in a way, left out the spatial degrees of freedom and eventually other quantum numbers like spin, and simply encoded these degrees of freedoms in expressions like these integrals, which then can be looked up in a table. Okay? So the question now is, how did we actually get this expression here? Because where we started in the beginning of the semester, we started actually with an expression like this, where this quantity was given by the sum over the number of particles, and then we had a H0, an operator, and as a function of the coordinates of a specific particle. And we know that this one could be translated into the kinetic energy operator, which is a second derivative, plus eventually some kind of external potential. And we are often going to write external here. So when we say external, it could be a harmonic oscillator which traps a particle, or it could be the Coulomb attraction between an atomic nucleus and an electron in, for instance, atomic neon. So before we show that expression, so we are going to make the translation from H0 in the what we normally call the coordinate representation, or what is what I would say wrongly called first quantization, and then into second quantization. So sometimes it's difficult to avoid saying second quantization. I don't like the naming, but it's something which is stuck with in the literature. Now, in order to do this translation here, we need to remind you of something which is called the spectral decomposition of an operator. Does that ring a bell? Okay, I can see from many of you that it didn't ring a bell. So let me remind you of that, because it's a way to represent an operator which is very convenient and very handy when we are dealing with quantum mechanical operations. So let's just have a short reminder on that, because else you may have the feeling that the equation I'm setting up now is just something which I pull out of a hat. So decomposition. So let's make an assumption now. So we have an orthogonal and normalized basis. And this basis is then given by some indices I. So we have all these states here, which we are assuming now to be orthogonal states. So we would then have some I from 0, 1, up to n minus 1. And one of these states is simply given by this. Then we assume now that there is an operator. So we have an operator A, which has this basis as an eigenbasis. Has this I as an eigenbasis. And then we know then that when we have such an orthogonal basis, we can expand a new function in terms of that basis. So if we now look at a state psi, this can then be expanded in this basis, alpha I of I here. And we know also that since this is a normalized basis, we know that the sum over all these coefficients squared, alpha I squared, has to be equal to 1. And you can see that if you calculate the norm of psi, and you want that one to be equal to 1, that simply leads to all these coefficients summing up to 1. I guess this is something you may have seen in courses in quantum mechanics. And if you've done linear algebra, you would have seen it there as well, except that then it's phrased a little bit differently. The next thing we do now is actually that we act with A on this basis which we have. So which means the same as us acting on n minus 1. Then we have this coefficient alpha I, and then we have A acting on I. So we know that this one is actually given by some eigenvalue, since I is an eigenbasis. So this is going to translate into something like this. But before we do that, let's add another feature. So what you could do now is to define a projection operator, or what I'm just going to call just a projection. So I'm going to define this projection operator as an operator which projects out the state J. And then I can act with this operator on the state psi. If I do that, then this is obviously simply J. So remember now that J times J, this operator is a matrix when we have a finite basis here, because it's an outer product of two vectors. And then what we have is simply this acting on the sum, and I'm skipping the subscripts, all the starting values, etc. for I. And we know that the basis is orthogonal, so that means that J of I is simply equal to delta Ij. So if I do the math then, this should simply be equal to alpha J. It projects out the component alpha J. So let's take a renewed look at the action of this operator together with the operator A. So let's do that. So it means that when I now look at this operator A acting on psi here, what we had is that this becomes equal to I equals 0 up to n minus 1. And then I have my alpha I, lambda I, acting on I here. Because I is an eigenbasis of A, I can rewrite this now as I equals 0 to n minus 1. And then I have a lambda I. And then I have this operator P of I acting on this state psi. This is just another way of writing what we have. Then, if you look at what we have here, that means that I can now recognize A as the sum over I equals 0, the eigenvalues multiplied with this projection operator. So this is the spectral decomposition of an operator. And this is something which is extremely handy. Okay. So you've probably seen this in some course, and but this is something which, if you don't use it, it's often forgotten. But we're going to use that now as a kind of intermediate step when we're going to make the transition from the coordinate space representation to the number representation of an operator. Okay. Any questions? So let's go back to what we had before. So we had a Slater determinant, which is our ansatz. And this is a function of x1, x2, up to xn, the number of particles. And then we may have some quantum numbers, alpha 1, alpha 2, up to alpha n. And this Slater determinant is written in terms of a basis. That basis is often chosen to be an eigenbasis of H0, the lower letter case. So we have alpha 1, x1, phi alpha 2, x1, and this goes all the way down to phi alpha n. So this could be an ansatz for the ground state. Now the next one here is phi alpha 1, x2, and this continues till the last particle, alpha 1, xn, like that. Like that. In second quantization, what we did then was actually to define it in the following way. So the same Slater determinant, same SD in second quantization. is then given by alpha 1, alpha 2, up to some alpha n here, which again is the same as A alpha 1, A alpha 2, up to some A alpha n acting on the true vacuum state. So what I'm going to do now is to act on the single particle states by using the spectral decomposition of an operator. So I'm going to bring in a definition which now follows the spectral decomposition. And I'm going to write this the way we would write it in the coordinate space representation. So I have an x of I acting on a phi alpha of I of x of I. So if you think back to these notes about the spectral decomposition, you have an operator acting on a state. Now, this is something which we then can rewrite in terms of a sum of alpha k prime. And there's going to be an alpha. So this is the integral, or what we might call the expectation value of the specific operator. So I put a prime here of h0. And then, so this is the integral, which we have defined before. And then I have phi of alpha k prime of x of I. So this is just us using the spectral decomposition of an operator. If I define that, now what we actually are looking at, so I'm going to look at this with no permutations. If I write this out, what we are going to get when we act with h0. So now I'm going to take the sum. I'm skipping some of the limits on these summations. And so what I'm going to have then is an h0 of x of I. So I'm summing of all these operators because now I want to look at the action of the whole operator, which is a sum of single particle operators. And this is now going to act on the way we have organized the Slater determinant. So in this specific case, there are no permutations, okay? So think back of the Slater determinant now as containing one term where we multiply all the diagonal elements. So when I do that, what I will have is something like this. So this is going to be a little bit boring exercise in keeping track of all the indices. Then I'm going to have an x1, I have a phi alpha 2 of x2, and this goes all the way up to phi of alpha n of xn. Now, if I use that formula, which we have on top here, this is now going to give us many, many contributions because we have a contribution from x1, x2, x3 due to the operator. So this is going to be now, first it acts on x1. So then we will have a sum where we now take the specific term with x1, and I can rewrite that in terms of an alpha 1, but prime. So I will have an alpha 1 prime, h0, alpha 1. And then I have my phi alpha 1 prime, x1. But the other ones are unchanged now because this is acting on x1 up to phi alpha n of xn. So this is essentially us applying this formula here to every single term in the Slater determinant. So you will see now that with no permutations, when we just take the product of the diagonal elements, this is now going to contain many terms. So there's going to be a new term here. So let me just write it down. So when it's acting now on alpha 2, we will have an alpha 2 prime with the decomposition of the operator, alpha 2, h0, alpha 2 here, alpha 1 with x1 is left unchanged, but now I have an alpha 2 prime of x2, and this goes all the way up to the next, to the final one, which is this one. And this goes on till the last element here, where we have an alpha n prime And then I have my alpha n prime h0 of alpha n, and then alpha 1 x1, alpha 2 x2, till the final term, which is an alpha n of xn. Like that. That was 0 permutations. Then we have the possibility of interchanging 1 and 2. So let's look at that one, and then you will start seeing the pattern for how we arrive at the final expression here. So if we now interchange x1 with x2, what we are going to have then, when we act with the operator h0, which is the sum of all these single particle operators, then I'm going to now act on phi alpha 1, but now I have interchanged, and I'm not looking at the signs, I'm just looking at the expression. So we have to keep track now that when we think of the Slater determinant, this involves actually a minus sign. But let's now just look at what happens when we act on it. So we have x1, and then we have all the remaining terms, alpha n to xn. When I act on this, what I'm going to get then is the following. So there's going to be an alpha 2 here, because now this is x1. So I will have an alpha 2 prime, and then I have an alpha 2 prime, h0, alpha 2 here, and then I have a phi alpha 1, x2, a phi alpha 2 prime of x1, because the first term is the one which acts on x1, times phi alpha n of xn. Then there's a new term where I now have an alpha 1, because now we have h0 acting on x2. So that is going to contain alpha 1 prime, h0, alpha 1. And then I have a phi alpha 1 prime, x1. Phi alpha 2 is now unchanged with x1, and all the way up to phi alpha n of xn. And this goes all the way up to the term with a alpha n prime. And I'm just putting dots here, where then I'm going to have alpha n prime xn. Okay, this is very exciting, okay? So if I compute now all the possible permutations, what we can do then is actually to rewrite the equations using the second quantization formulation and taking care of all permutation phases. What we can do then is actually to take all these expressions and rewrite them. So let me just wait a little bit. And so when you now look at all the permutations, and I'm not going to bring in all the permutations because that's going to be a pretty boring exercise. If you want to convince yourself, you could take a 2-particle determinant and a 3-particle determinant, and you see then how this is going to be. So by computing all possible permutations, these are all the possible ones, permutations, we can then rewrite, if we take care of the right sign, rewrite the equations using the more compact second quantization representation of a Slater determinant, and then taking care of all permutations, and the sign, taking care of all permutation phases, just to rewrite this one. Taking care of all like this, we can actually rewrite this as H0 acting on alpha 1. So now I'm bringing in the second quantized expression. and then I have an alpha n. If I do that, what I'm going to get is something as follows. So I'm going to get a sum over all the alpha 1s prime, and there's going to be a term of alpha 1 prime, h0 of alpha 1. And now I have alpha 1 prime, and then I have alpha 2 up to alpha n. So keep in mind now that now we are setting in the full Slater determinant. So the full Slater determinant means that we have taken into account all possible permutations. So this would continue then with an alpha 2 prime. So I have an alpha 2 here of h0 of alpha 2, and then I have an alpha 1, alpha 2 prime up to alpha n. And this continues all the way till the final term. So keep in mind now that this is just a full Slater determinant. In the previous case, we were just looking at the product of the single wave functions. Now, in this particular case, this alpha, which you see here, contains all the possible permutations we can have. So this is just a compact way of summing up all the permutations which we started to play around with here, where we simply just wrote down this case, and then we had the first case with no permutations, which essentially means that we are acting with these operators here on a full Slater determinant. Yeah? This line here? Last line, yeah.
The middle sum, alpha 1, should be x2.
So which middle term? This one?
Yeah.
Oh, sorry. That should definitely be x2. Yeah. This is just another case where you have it in front of you and then you translate wrongly. I'm not doing these things on purpose to see that people are awake, actually. Okay, so this is simply me writing wrongly off from my own notes here. So we would have an alpha n here, prime, and then we have an alpha n prime of h0 of alpha n, and then I have the Slater determinant again, alpha 1, a alpha 2, up to alpha n prime, like that. Now, we are not done because we can manipulate this further. So if you think of a Slater determinant, if you now look at, suppose we take one of these random Slater determinants, and if you look at an alpha 1, alpha 2, and then in the middle here, there's something like an alpha of k prime, and then we go up to an alpha of n. When we use second quantization, we can actually write this as an a alpha k prime dagger, a alpha k. And this is now acting on a state alpha 1, alpha 2, and then there's a slot here which is called alpha k, and then up to alpha n. So when we now act with this operator here, since this exists, then we are permuting all these operators. That gives a sign minus to the power of times we permute. But then we bring back into the same slot a new particle, but with quantum numbers alpha prime k. So such a determinant can actually be written out in terms of this operation, which you see here. So this is where we are now coming back. If you look at these terms, it means that every one of these can actually be written out as one creation operator and one annihilation operator. So what we can do then is to take this sum, which you see here, and then rewrite it in terms of creation and annihilation operators. So we would have an H0 acting on this state alpha 1, alpha 2. This is our original state. And then we have a term which goes like alpha 1 prime, and then I have an alpha 1 of H0 of alpha 1. And in this particular case, I have an A alpha 1 prime creation operator, A alpha 1, and then it acts on the original state, alpha 1, alpha 2, up to alpha n. That's a different way of rewriting the same term. Then obviously I will have a term over alpha 2 here, and then I have an alpha 2 prime H0, alpha 2, and then alpha 2 prime with the creation operators and alpha 2. And then we have the same Slater determinants. I'm just writing it like this. And this goes on in the last term, plus an alpha n prime. And then I have my alpha n prime of H0, alpha n. And then I have my A alpha n prime, creation operators, A alpha n, and acting on the same reference state which we have here. Okay, so this is something which we can rewrite now in a more compact form, because we have a summation over these alpha 1s here. So this is a summation, but we also have a summation here over alpha 1, alpha 2, alpha n. So that means that I can convert everything here into a double sum. So I can rewrite this in a much more compact way, and I can rewrite that as the sum over alpha and beta, where these are the basis states which we have chosen. And then I have an integral alpha H0 of beta, and then I have A alpha, A beta acting on this determinant alpha 1, alpha 2, up to alpha n. So this is equal to this H0 acting on this Slater determinant we have chosen as a reference state, or any Slater determinant. There's nothing which hinders us from doing that. So that means that we would then rewrite the operator H0 in second quantization as this double sum of alpha of H0 of beta and multiplied with A alpha, A beta. So this manipulation which you saw here is based on you using the spectral decomposition, but it's not so exciting. And it's going to be less exciting when we do this with a two-body operator. So in the two-body operator, I'm going to skip that from the notes here because we are getting close to the break. And if I do this after the break, you will all be asleep in 10 minutes. But you will find the derivations in the lecture notes. But essentially what you're going to do now is to manipulate the states, except that then you have a two-body operator. But you see the basic principle? So the basic principle is us now interpreting things in terms of the second quantization operators. And that allows us to obtain an equivalent expression for the operator in this new representation. And in what we often have, this is a pretty common case, is that alpha beta is an eigenbasis of this operator H0. So this is pretty common. So that means that this alpha can be, and it's often that the choice which we use when we are constructing a Slater determinant, that we already have an orthogonal basis, and often, pretty often, the basis is normalized as well. So this gives us a simplification of this sum in the sense that the double sum becomes a simple sum. So if you have that, then this operator H0, so if this is the case, then H0 is just a sum of alpha, and then you will have epsilon alpha, A alpha, A alpha. So last week, we did actually calculate some expectation values of this specific operator. Now, the other operator, which I'm just simply going to state now, is the interacting piece of the Hamiltonian, and that is given by 1/2. And then we have a sum over alpha, beta, gamma, delta. And we have the integral, which we defined in the very beginning of this lecture. And this has a gamma, delta, and it has a chain of creation and annihilation operators. This is often rewritten in terms of anti-symmetrized integrals. So it can also, you will also find it in this disguise, 1/4, alpha, beta, gamma, delta, where we then replace this one. And it's pretty easy to see that this is a viable approach as long as you bring in the definition of the anti-symmetrized matrix elements or anti-symmetrized integrals. And where this alpha, beta, just to quickly remind you of that before we take a small break, of AS is actually equal to the integral, or the direct term as we have called it, minus the exchange term. And this follows simply from the Pauli principle of delta of gamma. So if you can pre-calculate these quantities, it's often common then to lump them together into just one quantity. Because then when we are calculating expectation values, we don't need to evaluate two types of expectation values where we have this term involved and this term involved. We can just lump everything together. And you can see that this is the case if you now use the properties of these specific integrals. So we defined that, I think it was in the first week, towards the end of the first week. So I like to suggest we take a small break. This derivation is something you can find in the lecture note. And you saw the way we proceeded with the one-body operator. And this is going to give us some kind of driving rules together with Wick's theorem. So after the break, we are going to look at some applications to some cases we have seen before. Actually, last time we already started to sniff a little bit at some of these expectation values. So let's take a look at this again. Any questions? Okay, so I'm going to put on the pause of the recording. So the thing we are going to do now is simply to practice a little bit. And when we are bored with that or done with some practicing, we are going to switch back to Wick's theorem and then look a little bit deeper into it. So Wick's theorem, the way it's proved, is simply by induction. But let's now remind ourselves of some of the things which we discussed last week. So I'm going to write down Wick's theorem again so that we can actually use it. And then, as I said, we're going to prove it thereafter. So one of the basic operations we have is the so-called contraction. So the contraction is given by a pair of operators. So this has to be a pair of, for having something which is non-zero, it has to be a pair of creation and annihilation operators. So it is defined, so if you have an AI, now I'm switching to Roman subscripts, hope that's okay. This is simply given by this expectation value here, AI, AJ. And we know that this one has to be equal to delta IJ. Then obviously we have other contractions. And then we can just read off immediately when we look at this as a vacuum to vacuum expectation value. We see that this one has to be 0. So, but this is also a contraction. And then similarly, we would have an AI dagger AJ. And we see also that that one has to be equal to 0. So these are the 4 possible types of contractions which we can think of between 2 operators. So that's the definition of a contraction. Then we have a normal order product where we now have a chain of operators. And let's just call this chain of operators for the A, B, C, D, etc. So we have a chain of operators, A, I'm going to put hats on them, A, C, D, etc., up to some C, X, Y, something like this. And this is now going to be organized so that we have a permutation according to the number of times we need to flip creation and annihilation operators, so that we will have a box here which contains only creation creation operators. And then to the left here, we have only annihilation operators. So let me just remind you of some of the simpler examples which we looked at last time. So I hope you can forgive me if I keep repeating some of the basic things. So a typical example which we had last time was an operator where we had a string of let's say we have an A1, A2, A3 dagger. And when we normal order this one, then we are going to switch A3. So we're actually using the anti-commutation rules. Using the anti-commutation rules gives us also some contractions, but when we have only the normal ordered case, this would then be -1 to the power of 2. And then we have A3 dagger, A2, no, so A1 and A2. So in principle, this is a little bit sloppy notation because this is an expectation value. So I should actually write this as a -1 to the power of 2, and it's a 0, A3 dagger, A1, A2. And we see that this is immediately equal to 0. So that means that when we reorder a chain of operators, we have a sum over different types of normal ordering, which give us automatically 0. And we don't even need to look at those terms. So Wick's theorem, which we showed last time by paper and pencil calculations for 1 and 2 pairs of operators. And we always have to have pairs of creation and annihilation. And you see that immediately from these commutation relations here, that if we have just creation operators or annihilation operators, so the creation here and annihilation, this is automatically 0. So we need to have the same amount of creation and annihilation operators. And these contractions go between pairs of operators. So that means that when I calculate an expectation value here of some chain of operators, now I'm just going to leave this unspecified. And then I have some X, Y, Z, W, something like this. When we look at Wick's theorem, I can use more colors now. This is the same as the normal order product. And you saw last time that we could, in the beginning of the previous lecture, that we could have this in terms of various definitions. So we could have this colon, etc., etc. But I'm just going to write this in terms of the n. And then we have X, Y, Z, W, like this. And then we have the sum over all possible contractions of one pair of operators. So the 1 here is just the sum over all the possible paired operators which are contracted of the same chain of operators. CD. So one of the contractions could be this one. And then we simply have to look at the sum over all of them. And we saw that explicitly with the example last time when we had 2 creation and 2 annihilation operators, that we got several contributions with 1 contraction, and then a term of a pair of operators which was normal ordered. Then this continues with a sum over all possible contractions of 2 pairs. CD, X, Y. And then we have 2 operators which now are contracted, but 2 pairs of operators. That's more correct to say. Not 2 operators, but 2 pairs of operators. And this goes on all the way till what we defined as the sum over n operators divided by 2. So that means that n has to be an even number. Because if n is an odd number, there will be an operator, either creation, annihilation, where you will simply have something like this, or if n is an odd number, so this is not paired with anyone, and these are automagically equal to 0. So let me just take this out here. So n has to be an even number of operators, and we have to have the same number of creation and annihilation operators, because else it will again give an expectation value which is 0. So this is again the same chain of operators, A, B, C, D, X, Y, Z, W. But now all the guys here are contracted with somebody. And we just indicate that one in this specific way. And the only term which survives, so this expectation value, is actually given at the end because all the other ones give us 0, because then we have a normal order product and there are some operators acting on the vacuum state. And since that operator is an annihilation operator, that simply gives us 0. So there's only one term which is left. And we saw that from the contractions which we did last time. So that's the only one which survives. So let's now look at an example. Last week, we calculated the expectation value of H0. And we also calculated the expectation value of the number operator. But what we did not was to calculate the expectation value of the two-body operator. So let's take a closer look at that. And let's now assume that we want to calculate in the lecture slides this week, you will see an example on doing this without Wick's theorem. And that is something which we normally call a pretty boring and painful exercise because it's so easy to mess up the indices. So let's now take an example and let's assume that we have just a two-body Slater determinant. And this is now given by two states here, and we just label this as 1 and 2. So which in second quantization is A1 dagger, A2 dagger acting on 0. And now, last time we calculated A1, A2 of H0, of A1, A2, and we assume that this A of I of H0, so I'm just reminding you of that, is given by delta ij of epsilon I. So what we found last time is that this one was equal to epsilon 1 plus epsilon 2. If we took away H0 here and simply put that to 1, then we had the number operator, which we also calculated last time. So let me quickly remind you of the things which we did last time. So this is a sum over all the single particle states which we have, 1 up to the dimension of the single particle states, AI. Actually, we don't use that symbol. I'm using this little n to indicate this is a number of single particle states. So that gives us simply, when we acted on a state, it simply gives us a number of particles which are present. Okay, so these are things which we did last week, but let's now try to fill in the gap which we had, and let's calculate 1, 2 of H of I of 1, 2 here. So this is when we write everything out. This is going to give us a sum 1/2 of alpha, beta, gamma, delta. And we have the integrals. And now I'm just using the notation where I'm not employing this anti-symmetrized matrix element. Delta, like this. And this is multiplied with the vacuum state. And then I have my A2, A1. And then I have my A alpha, A beta, A delta, A gamma. And this is now acting on the state, on the ket side, like this. So it's pretty common when you analyze these expressions to leave out temporarily this sum here and this element, and also take away 0, and simply look at the possible contractions you can make. So in this particular case, we know exactly that, using Wick's theorem, that there is only the term where we have contracted all pairs of operators, creation, annihilation, which gives us something which is non-zero. So let's now look at the possible contractions which we can make, okay? And we are going to get back the result which we had earlier. So I'm just going to shift page here, and I'm going to take away the vacuum expectation values, no, the vacuum states, and also the sums, and we are going to focus only on the operators. So this is pretty common because it takes away a lot of clutter in the equations. So let's just look at one contraction where we have one set of contractions. So what I could do now is to perform this one. So these are two operators close to each other. So I perform that contraction and that one. So this is obviously going to give us delta gamma 1 multiplied with delta of 2. Now, when I said all contractions, this is just one of the many ones, but there will be many which are 0. So we're not going to list the zeros. I mean, that's just waste of time, right? So the next one, which we could have, is actually this one, and then finally that one. So when we look at the contractions we have then, this will be delta beta of 2 multiplied with delta alpha of 1. Now, I could do contractions of this type as well. There's nobody which hinders me. That is one of the many contractions I can make, but I know that this is 0. So the only non-zero ones, if we just spool back a little bit, so if we look at the contractions with respect to the true vacuum, these are the only ones which we have, and this guy is the only non-zero one. So there is no point in calculating zeros, right? We just drop it. So when I list the contractions here, I'm only going to list those which are non-zero. Now, when we are going to introduce a new vacuum, a reference state, then we are going to find it handy to redefine this one with respect to a new vacuum. And this is something we will discuss a little bit more in detail next week. It's called the particle hole representation. But let's now continue here and look at the possible contractions. So let's now say that we keep this one. So let's just keep that. But then we have another contraction here, which is actually this one. Now, in order for us now to have this operator being contracted with that one, then we have to interchange, or one interchange we can do is just to flip these two, and that gives rise to a minus sign. So if I switch these two using the anti-commutation rules, then I'm going to have a contraction of beta 1. So this is actually going to be delta beta 1 and delta alpha 2. So when you draw this now, the way I've set it up, every time you have such a crossing contraction line, you can think of that as giving rise to a minus sign. So many of the things you do in many body physics, they become very pictorial. But this kind of pictorial calculational rules, they follow actually from the basic contractions and usage of anti-commutation relations. Now, the one which we had here stays the same. So delta gamma 1 and delta 2. So the first term, if we take this one, so let's take a small, do a small intermediate step here. This is going to give me this integral, 1, 2. Then this guy here is going to give me minus. And now I have 2, 1 of V, 1, 2. Because now just think back that I had the original expression alpha, beta, V, gamma, delta. So the Kronecker delta is now picking out one specific value of gamma. So that means when we have these 4 Kronecker deltas, that means also that when you look at the sum here, obviously since you have 4 Kronecker deltas, the sum just reduces to one element. Okay? Does that sound okay? So if we now continue along this path here, we can then change things again. So let's suppose now that we have this one as before, that contraction, but then we interchange this one, so delta goes to A1, and you see we get a minus sign again here. So this would be delta beta 2 of delta alpha 1. This would, on the other hand, give us delta gamma 2 of delta delta 1. That gives us an integral which goes like 1 to V to 1. And then you see that there is a final result here, which I'm going to mark like this. So it will be this contraction. So these are the only non-zero contractions. So I keep that one, and I keep this one. So this is going to give me delta gamma 2, delta delta 1. And I'm going to have here delta beta 1 and delta alpha 2. And this is going to give me 2, 1, V 2, 1. Now, one thing which we said the very first week is that the type of operators which we have, they are invariant under the interchange of 2 particles. These are also identical and indistinguishable particles. So that means that for us, this guy here is the same as 1, 2, V 1, 2 if I interchange particles 1 and 2. If I do the same here with this integral, that one is going to be the same as this term. So I'm going to have 2, 1 of V 1, 2. So I get then 1 here and 1 here. I have a factor over half in front here. 1/2 plus 1/2 gives me 1. And the same happens with the other term. So when I collect everything, what I'm going to get then is that this expectation value of 1, 2 is going to be exactly what we calculated before. 1, 2 here is going to be equal to 1, 2 of V 1, 2 minus, and then I have 1, 2 V 2, 1. And we could rewrite this in terms of an anti-symmetrized matrix element, which we then would rewrite like this. So let me just quickly remind you of that. This matrix, or this integrals, it's a sum of integrals, has the properties that it's equal to 2, 1, V 2, 1. Anti-symmetrized, it's also equal to minus 1, 2, V 2, 1, anti-symmetrized. And it's easy to see that from the definition of this element here. And again, this is equal to minus, and this is 2, 1 of V 1, 2, anti-symmetrized. So when you're storing these objects, these integrals, it's pretty common actually to use these anti-symmetrized integrals, because then instead of storing both this one and that one, you would just simply store 1. And that saves memory by a factor of 2. Sometimes you cannot do it. Sometimes you would need to evaluate both the direct term and the exchange term. Any questions so far? So you see the usage of second quantization, which then with Wick's theorem gives us a very compact calculational rule. So assuming that you have already calculated the integrals, then you can easily set up the given expectation value. Now, there's something which I wanted to mention before we start with a diagrammatic representation, and then Wick's theorem. So the calculation here seems pretty straightforward, and I hope I've convinced you a little bit that Wick's theorem gives us a handy way to calculate expectation values. You can see that if we now just take a look back at the slides, because in the slides you will find an example of the way you would calculate this without using Wick's theorem. So let me just bring that up here. So in the slides, there is an example where we perform that calculation, which we did now. So I now just have a label beta 1, beta 2, and these are different states. If you do that with the standard anti-commutation relations, then you would have to keep track of all these different operations. And you see that some of these are going to give us a product of operators. So this will be normal ordered. So this is automatically 0 because you have an annihilation operator which would act on a vacuum state, which gives us 0. This would give us 0. This term here, when you interchange it again, would give 0. This term here gives automatically 0. So there are many of these which then, when they are baked into Wick's theorem, they arise as the result of either one operation between contractions between a pair of operators, or like when you have two Kronecker deltas, this is two pairs, etc., etc. So you can keep elaborating this one again and again, and when you've gone through it, you should arrive at this expression here, which is essentially the same which we went through here, except that now we have made, instead of the states 1 and 2 being the same on the Brown-Niket side, we are now having two different states. But when you run this through, you would actually have to grind through all the anti-commutation rules and applications to the different operators. So in this specific case here, I actually skipped many small intermediate steps. And it's very easy to make errors. So Wick's theorem saves the day for us in the sense that we are actually going to get expressions which are easier to calculate because we only need to take into account what we called the final term here. So this is just Wick's theorem restated here. Okay. However, we are going to see pretty soon now that even with this compact formalism, it's going to become unwieldy when we have many particles. Because clearly, if we now go on to, let's say, a new Slater determinant, and let's do that. So let me just do that one. So suppose now that we look at a new case. So we have a new state, which we could call 1, 2, 3, 4. And this is given by A1 dagger, A2 dagger, A3 dagger, and A4, acting on a true vacuum. Now, clearly, when you're calculating the expectation value of this specific state, you would have to set up 1, 2, 3, 4. The two-body operator is the one which actually causes problems. The one-body operator is pretty easy to set up. And you will see that when you calculate in different exercises. So in this specific case, what we would have to evaluate is still this sum over alpha, beta, gamma, delta. We have this integral, gamma, delta. But then this is multiplied now with the following. So I would have an A4 annihilation, A3 annihilation, A2 and A1 annihilation, and then I have an A alpha, A beta, A delta, A gamma, and then I have an A1 dagger, A2 dagger, A3 dagger, and A4, multiplied with a vacuum state. And now you see clearly that you have to run over all the possible contractions here as well. And this is starting to get a little bit more complicated, okay? And so the bookkeeping becomes pretty boring. And the question is, can we actually reformulate this in terms of a new basis? This leads to what we will discuss next week. So we can redefine the vacuum. So even if we have a formalism which looks pretty simple, it quickly becomes unwieldy when we have many particles. So redefine vacuum 0 to something which we are going to call a reference vacuum, which I will often label with a C, because it's often defined in terms of a core. That means that we fill up some specific single particle states, and we look at excitations with respect to that one. In that specific case, which we will detail more next week, we can then simplify the calculations, because often the operators which we deal with, they act on at most 2 to 3 particles at a time. So by redefining the vacuum, we can then avoid this, so that perhaps this state now, we could think of these 2 states here being frozen in some way and redefine a new vacuum. And then we would act with a 2-body operator only on these states. And we will see that next week, that gives us an even more compact and, from a calculational point of view, powerful and also handy way of evaluating expectation values. You see quickly now, if I give you 100 particles, and if you were to take home an exercise with that, you would hate me forever, because you don't get any new insight there. So redefining the vacuum is actually something we will do next week. But I thought of stopping today with something which is going to be very, very easy for us in order to interpret physical processes. And this is our first introduction to a diagrammatic representation. So let's do that. And let me look at my cheat sheet here, so I remember what I was planning to say. Yeah. So the diagrammatic notation, and we are going to introduce some parts of it, and then we will continue with that when we are getting more complicated expressions. So let's now define the first expression here. So we have an A alpha contracted here. So this is often, in terms of diagrams, it's often written like this. So I have a state alpha, which gets contracted with a state alpha, and I put this sign here, but often I skip it. I just leave the arrow. So the arrow pointing up here up represents and now we're just dealing with particles all the time because we have the true vacuum. So we add a particle on top of the true vacuum. So this represents the arrow pointing up represents a particle on top of 0. 0 here. So in our case, with the true vacuum, later we are going to introduce whole states, which are states below the Fermi level. So for those of you who may have taken a course in quantum field theory, the whole states would be something which mimic what you have encountered as antiparticles. So with true, wait, what was I going to say here? On top, yeah, with a true vacuum, a true 0, all states are particle states. So all the single particle states, all states are particle states. Then, if I look at a one-body operator, there is a way by which we can represent it graphically. So a one-body operator is the next step. And when you have not done contractions, it's common to not put arrows on the lines here. So we have a one-body operator. And let's take an example with H0, which we have written as a sum over alpha beta. And then we have alpha, H0 beta. And then we have A alpha, A beta. So the way you can think of this now, if you look at the specific matrix element or integral which you have, we are going to call beta an ingoing state or incoming or outgoing, and then alpha is going to be the outgoing state. So the way you could think of this now, suppose you have a nuclear reaction between a proton and a nucleus. So you could think of a nucleus which is oxygen 16. I'll write it like this, 16O. And then you have a proton which comes in so this is the incoming state or ingoing. And then it reacts with this nucleus. And then you have an outgoing state. And we could label that with a P prime. So P for a proton. So it comes in with a specific energy, some specific quantum states. It interacts with these 16 particles. It modifies its energy through the interaction. It may even have different quantum numbers. And then it leaves and is the outgoing state. And this could be rephrased in terms of one-body operators. So you can think of another example is an electron seeing an atomic nucleus. So you could replace this example here, with another example where you have an electron E minus, and then you have atomic neon here. So this electron gets closer to atomic neon. It interacts with the 10 electrons plus the 10 protons. And then, so this would be your ingoing state, in. I just write it like this, in. And then you could have a new state, an E minus prime. And this is the outgoing state. And in the case of atomic neon, we have assumed then that we can think of this H0 as the attraction from the atomic nucleus plus the kinetic energy of a given electron. And then you would simply set up a model like this where you would calculate these expectation values. So this is often translated in a diagrammatic way. So this specific operation, which we are setting up now, so when we are defining this operation of alpha beta, of alpha H0 of beta, of A alpha, A beta, when we write it diagrammatically, it would then be translated into something which looks like this. So normally when you put arrows on it, you're assuming that a contraction has taken place. So when I leave out arrows, I'm just thinking of the operator itself. So keep in mind now that when like in this case, I defined a contraction to have an arrow sign here. So when I leave out the arrows, I'm just going to label the states, and then I will normally, but this kind of convention is something which is broken by different authors, so there's no kind of standard convention here. But this is one of them. So you would have an incoming state here, beta, would be represented like that. So you have a beta, and then you label the interaction. So this would correspond then to the specific element which you're looking at, H0 of beta. And then you have the outgoing state alpha here. So when I then calculate an expectation value, so when I calculate, let's say, this expectation value with 1 and this H0 with a state 2 here, And I'm assuming now that the single particle basis is an orthogonal basis of that operator. What I would get then, or rather we can just keep it like this, what I would get then would be a 1 of H0 with 2. So you don't need to assume that you have an orthogonal basis, which is an eigenbasis of H0. So I'm just setting up two states 1 and 2. In that specific case, what we would do then is to write this out in terms of an arrow, because now we have performed a contraction with alpha, because this is the same as 0, A1, A alpha, and then I have A beta of A2 dagger of 0. So this is being contracted, and this is being contracted. Then you would typically put arrows, and you write 1 here. You have the incoming state, which is the state 2, and then you have the outgoing state, which is 1. So when you see arrows, some authors, but this is not consistent, but some authors would actually put arrows because then a contraction has been calculated. If you just want to depict the operator itself, you leave out the arrows. Okay? So that's one type of notation which we are going to use. So that means that the outgoing label, in this specific case, outgoing label is now given by the state alpha. And then the incoming or ingoing, let's write this incoming label, is then given by this ket state beta, which we have here. Let's now look at the two-body state. Okay. So this is rule number 3 or definition number 3, which is perhaps better. So let's look at the two-body operator. In that specific case, what we have now is a sum of alpha, beta, gamma, delta. There's a factor of a half, and then alpha of beta, of V, of gamma, delta. And then I have an A alpha, A beta, A delta, A gamma. The way we would write this operator is now as follows. So we would indicate the interaction like this. If you're doing particle physics, you will also have time in it. And then you would call this a vertex. We also call this a vertex. So this is part of the two-body interaction, and they have so-called vertices. Then what we have here is a state which we label as gamma. So this is an incoming state. So you see that we are going to have a convention that the state to the left, the first state here, is in the left of the diagram. And then we would have an alpha here. And then we would have a delta coming in here. And then a beta coming out here. So what you have then is a kind of ordering. So this is the outgoing state, alpha, beta. So this is left. And this is right in the diagram. So this is the outgoing. And then we have the incoming. And then we would have a gamma of delta. So this one would be to the left in the diagram. And this would be to the right. So then we have a visual picture where you would simply say now that there is an interaction between two particles where they are in the state gamma and delta. And then there is a transition probability where they go over to alpha and beta. And then instead of writing down all this stuff here, you simply write down a diagram. Okay? So that becomes very handy. So let's now look at the state. So a given state. So this would be 4. With the true vacuum. So there's no reference vacuum here. So what we would have then is something like an A1, just to give an example, A2, A3. like this. This is you making 1, 2, 3. Now we are keeping the operators. So what you would simply draw then is 3 lines without putting the arrows, 1, 2, 3. So this would be a way you would represent your state. Now, when you're acting on with an operator on that state, so you can think of the next step, and before we take a break and wait till tomorrow, action of H0 on that state. What we would have then would be something like this. So we would write this diagrammatically. And so we start with 1, 2, 3. And then we have the operator, which we will simply put in here, in between. And that has some alpha and beta. And finally, we have the outgoing state, which I'm just going to call 4, 5, 6. Then we are going to run the contractions. So the first possible contraction is that we have 1 with alpha and 4 with beta. Then there is nothing for 5 and 6 and 2 and 3, except that they join forces and they go down like this. There is a new contraction. Then we would write everything in the following more compact way. We would have 1 here, we would have 4 here, and then we would have 2 Kronecker deltas. So which we would simply write like this. So we normally skip these contraction signs. So this would simply be delta 2, 5 and delta 3, 6. Now the Kronecker deltas are normally left out because they're just ones. And you would simply keep this guy here. So you see that now what you can do is to combine all the different legs. And when you combine all the different legs, you can combine this one with that one, this one with that one, etc., etc. And this is a way by which you can then get all the contributions. Because when you look at this one now, you would read off that this one is nothing but 4, H0, 1, multiplied with delta 2, 5, delta 3, 6. And normally you leave those out. So in this kind of pictorial way, you can think of a process where you have 3 particles in a given initial state. There is an operator which acts on it. And then you have a final state, which is now 4, 5, 6. And you would simply illustrate that by a diagram. And these diagrams are normally called Feynman diagrams. So these are the kind of driving rules which we're going to elaborate on. And it gives us a very compact way to represent physical processes. So how many of you have met this kind of things before through quantum field theory? Yeah, I can see. Good, good, excellent. Okay. Should we take a break till tomorrow? Everybody's ready for a break. I can believe it.